Hi, this is Introduction to Systems Thinking, and we'll be going over what it means to take a systems approach. So to start out, what is a system? Well, there's a difference between a heap of disconnected parts and a system that has many different components working together to do something. In this illustration, the bike parts work together to serve a certain purpose. And there's another distinction here I want to highlight, which has to do with the question, what is a complex system? So there's a difference between a machine, which has parts that work together in a predictable, defined way, and something like an ecosystem, which also has parts working together, but that also exhibits properties like self-organization and emergence. Now, for both of these systems, you could say that the whole is greater than the sum of its parts, but the kind of order in these systems is very different. With a bicycle, the order is top down, it's sort of prescribed into the way the system is built, how it works. And that's decided in this top-down way from the designer of the system. Whereas with the ecosystem, the order sort of emerges from this interactions between the different species in their environment. So for the ecosystem, you can look at properties like resilience, which is how easily the system bounces back from a disturbance. So there's another way of thinking about the difference between simple versus complicated versus complex systems. And these distinctions aren't perfect, but they serve as a good rough illustration. So we could say that baking a cake is a relatively simple thing. You get the ingredients, and if you follow the recipe, you can reasonably expect a certain outcome. Now, constructing a building is much more complicated. There's many moving parts, and the recipe or blueprints look very different, but there's still a plan, and if you follow it, you can expect to get certain results. And raising a child, on the other hand, is very different. So there's no instructions that you can follow that will lead to a predictable outcome. And as any parent will tell you, you have to be adaptive to the changing needs of your child and largely figure it out as you go along. So being able to change the behavior of a child to the extent that that's even possible depends on understanding the factors underlying their behavior. And this distinction is good to keep in mind as we consider complex social issues. Now, social change is difficult because people are complex, both at the individual level and at the group level. And that's not to say that change is impossible, but we need to try to understand the factors underlying complex social systems in order to locate leverage points for changing them. So why systems thinking? Well, it's very difficult to anticipate the behavior of complex systems. Our brains are just not built to understand nonlinear behavior. So our intuition often leads us astray. Maps and models and other heuristics, which are tools for thinking, can help us understand the behavior of complex systems. So what does systems thinking look like? It can be lots of different things that fit into a few general categories. Most broadly, systems thinking is a general orientation or approach that emphasizes the importance of considering how parts of a system interact to produce this larger behavior. Systems thinking can also be heuristics or strategies for thinking differently about problems. So this could be strategies to help you see how things are interrelated. So what the boundaries of the system are, how people have different perspectives depending on how they're positioned in the system and how systems change. An example of a heuristic is the iceberg model. And then of course, systems thinking can also mean maps or models that are used for examining in a more precise way how systems work. Now you can distinguish systems thinking from more traditional reductionist thinking. And this diagram shows some of those differences, the distinction between disconnection and interconnectedness, linear and circular thinking, silos and emergence, parts and wholes, analysis and synthesis, and isolation and relationships. And I'd like to emphasize here that systems thinking isn't necessarily superior to traditional reductionist approaches, it's just different and serves a different purpose depending on your research question or what you're trying to accomplish. So in science, for example, sometimes we need to take an analytic approach and use a scientific method to look at a certain component of a system or a relationship between two things. In that kind of approach, you want to try to control for variation so you can isolate that one specific thing. And that's great for learning about that one piece. And that can work in concert with systems approaches that really try to take a broader view and say, okay, how do all those different pieces that we know about work together? And how can we wrap our heads around that variation or messiness to understand the big picture? An important concept in systems thinking is mental models. So Peter Senge, who has written a lot about the topic, says that mental models are deeply held internal images of how the world works, images that limit us to familiar ways of thinking and acting. Now, mental models can be individual or shared, and they're often below our conscious level of awareness. They can be based on experience or assumptions and shape our perception, reasoning, and behavior. They can also be difficult to change. Mental models can also be wrong. So here's one of my favorite examples of this idea. So there's a guy reading the newspaper and he says, shouldn't we make the hole in the ozone bigger to let out all those greenhouse gases? So you can see that he has a certain set of assumptions about how the climate system works that are wrong, and that those wrong assumptions lead him to a bad policy suggestion. So mental models are really the reason we build systems maps or models. So in her book, Systems Thinking, which we'll be looking at in this course, Donella Meadows talks about the value of, quote, getting your model out there so you can make your assumptions or beliefs visible to yourself and to others and to change them if needed. Let's talk a bit about what systems mapping and modeling is and why we do it. So when we use systems mapping and modeling, we're trying to understand problems and potential points of leverage for change by examining how things interact and how they change over time. And this is a tool for better understanding your own and other people's mental models. And there's a range of different kinds of diagrams or maps or simulation models, and I use the term model to refer to any of those. Now here's a few examples of systems maps or diagrams. First is the iceberg model. And causal loop diagrams, we'll be looking at both of those in this course. Here's an idiosyncratic kind of visual diagram someone made to illustrate a system. Impact gaps canvas is an example. And here's some examples of network models. And the types of map or model you use depends on your research question and the sort of system you're dealing with. And in this course, we'll focus mostly on causal loop diagrams, but we'll touch on some other models, and we'll also discuss how to match a certain approach to your research question. And that concludes this video. Thanks for watching.